Hello and welcome. This presentation focuses on the AI-enhanced creation of digital twins from iPhone LiDAR for immersive extended reality experiences in NVIDIA Omniverse. The work highlights how everyday mobile LiDAR data can be automatically reconstructed, enhanced through artificial intelligence models, and rendered as realistic interactive digital replicas inside immersive environments. Let's begin with the introduction. In recent years, digital twins have evolved from static visual replicas to intelligent semantic aware systems. However, achieving high quality 3D reconstruction using consumer grade LiDAR remains a major challenge. Neural Radiance Fields, or NeRFS, deliver remarkable visual realism but lack semantic understanding. Conversely, large vision language models provide rich contextual reasoning but have limited spatial grounding. This creates a key research gap. No unified framework currently integrates semantic intelligence, high fidelity rendering, and accessibility within a single pipeline. To address this, a novel NeRF LVLM framework is proposed, combining NeRF's photorealism with the semantic capabilities of large vision language models for real time, intelligent digital twin creation. This work introduces several core contributions. First, a unified NeRF LVLM framework is developed to achieve semantic guided, high fidelity 3D reconstruction. Second, real time ray tracing and DLSS optimization are integrated to enable efficient photorealistic rendering. Third, OpenUSD export ensures interoperability and seamless visualization inside NVIDIA Omniverse XR environments. Consumer grade LiDAR data from the iPhone 14 Pro Max is employed to promote accessible 3D modeling. Quantitative benchmarking demonstrates measurable improvements in PSNR, SSIM, and LPIPS scores. Finally, the system's applicability is validated across multiple domains, including XR environments, healthcare, and robotics. Next, the related work is reviewed to situate this study within current research trends. Existing literature reveals several distinct directions. NeRF and NeRFacto models provide impressive visual realism, yet their understanding of semantic context remains limited. Large vision language models, while capable of strong reasoning, lack the spatial grounding necessary for accurate 3D reconstruction. Digital twin applications in robotics and healthcare achieve precision but often struggle with scalability and semantic coherence. Visualization platforms such as NVIDIA Omniverse or Unity enable immersive inspection but typically operate in isolation from semantic reconstruction pipelines. From this comparison, a clear gap is identified on the absence of a unified, semantic aware, real time framework that integrates high fidelity rendering with intelligent reasoning. The proposed model is now introduced. The proposed framework integrates the full pipeline of data acquisition, encoding, semantic enhancement, rendering, and XR visualization. Data are first captured through iPhone LiDAR scans using Polycam, then organized for processing. A ray bundle encoding mechanism generates spatial rays and samples that represent 3D geometry. Next, a large vision language model, specifically GPT-4, is employed to enrich these features semantically. Neural volume rendering with DLSS optimization is applied to produce photorealistic results, while OpenUSD export ensures interoperability across XR platforms. Finally, real time visualization is achieved inside NVIDIA Omniverse and MetaQuest 2, enabling immersive inspection of reconstructed scenes. In this system, a frozen GPT-4 model functions as a semantic prior. Deterministic prompts are used to refine the visual features extracted from the LiDAR-based NeRF encoding. The resulting enriched embeddings are mapped back into 3D space and concatenated with NeRF positional encodings. This approach ensures reproducibility and efficiency while improving adaptability across different domains. Through the integration of NeRF's visual fidelity with GPT-4's semantic intelligence, the model achieves both realism and contextual understanding in digital twin generation. Next, the experimental setup and evaluation results are presented. The experiments were conducted using an NVIDIA RTX 4090 GPU with 24 gigabytes of VRAM under CUDA 12.6. The dataset consists of iPhone LiDAR scans captured through Polycam, focusing on indoor environments. Training was performed for 30,000 iterations using the Atom Optimizer with a Cosine decay scheduler. Evaluation metrics include PSNR for reconstruction accuracy, SSIM for structural similarity, LPIPS for perceptual realism, and FPS for runtime efficiency. Comparisons were made between the baseline NeRFacto and the proposed NeRFacto LVLM frameworks across both human and robotic digital twin scenes. All visualizations were carried out in NVIDIA Omniverse for real-time, ray traced inspection. Quantitative results reveal that integrating the large vision language model improves PSNR by approximately 3%, SSIM by 7%, and reduces LPIPS by around 2%. The Nerfacto LVLM human digital twin variant achieves the highest overall fidelity and perceptual realism while maintaining consistent performance across both human and robotic datasets. Ablation studies confirm that LVLM integration enhances semantic consistency with minimal computational overhead, less than 1%. The human digital twin configuration provides the best balance between fidelity and realism, whereas the robotic variant achieves superior runtime efficiency. The trade off curve demonstrates a stable balance between semantic gain and computational cost. Qualitative comparisons further validate the improvements. Depth maps show sharper boundaries and more precise geometric edges. Accumulation results exhibit reduced artifacts and smoother surface uniformity. RGB outputs display greater realism, texture coherence, and consistent color representation. Overall, the Nerfacto LVLM human digital twin achieves the most photorealistic and semantically aligned reconstructions. The reconstructed twins were rendered inside NVIDIA Omniverse using USD Composer with real-time ray tracing and DLSS acceleration. OpenXR integration allowed immersive VR inspection through MetaQuest 2. Three key scenes were visualized: a robotic avatar under physical lighting, a human avatar in desktop mode, and a combined XR scene featuring both avatars in a shared environment. Performance analysis shows real-time rendering sustained across both desktop and XR modes, with less than 5% reduction in frame rate under full ray tracing. DLSS and a foveated rendering maintained high visual fidelity while reducing computational load. Consistent lighting and adaptive resolution scaling ensured perceptual parity between desktop and immersive XR visualization. The discussion now summarizes performance insights, domain implications, and potential directions for future work. The Nerfacto LVLM framework successfully bridges visual fidelity and semantic understanding in three-dimensional digital twin reconstruction. Integrating large vision language models leads to a consistent performance boost. PSNR increases by 3%, SSIM by 7%, and ray throughput by nearly 3%, while maintaining real-time rendering at approximately 38 frames per second on the RTX 4090. These results confirm that the proposed architecture enhances both the realism and the semantic depth of reconstructed scenes without compromising efficiency. The framework's potential extends across multiple domains. In healthcare, it enables photorealistic anatomical simulation for surgical training. In robotics, it supports semantic mapping and adaptive navigation. In the metaverse and extended reality environments, it allows immersive behavioral training and task rehearsal. And in urban simulation, it can facilitate large scale digital twin modeling for infrastructure planning. However, several limitations remain. Real-time fidelity currently depends on high-end hardware such as the RTX 4090 GPU, and the framework relies on high-resolution RGB and LiDAR inputs. Moreover, the present implementation assumes static scenes, limiting adaptability in dynamic environments. Future work aims to enhance interactivity and emotional realism. Planned extensions include integrating NVIDIA ACE and audio two-phase for real-time speech and emotion rendering, developing multi-agent human-robot co-learning systems, and implementing facial stress detection using OpenFace 3.0. Further directions include emotion-aware avatars within Omniverse, multimodal fusion of wearable and audio data for richer sensing, and adaptive LVLM tuning with live sensor streams to support continuously evolving digital twins. Finally, the conclusion summarizes the core contributions and future vision of this research. The proposed Nerfacto LVLM framework unifies neural radiance fields with large vision language models to achieve semantic-guided, high-fidelity 3D reconstruction. This integration improves both visual quality, including PSNR, SSIM, and LPIPS, and runtime efficiency. Through seamless interoperability with NVIDIA Omniverse, the framework enables immersive, real-time simulations across domains such as healthcare, robotics, and smart cities. By combining realism, intelligence, and scalability, it establishes a new benchmark for accessible and semantically enriched digital twin systems. The next steps involve extending the model toward dynamic scene adaptation, temporal consistency, and large-scale XR deployment, paving the way for real-time, intelligent environments that evolve continuously with their physical counterparts. Thank you. This work bridges AI, 3D reconstruction, and digital twins towards smarter immersive systems.